To week 9, lecture 22, memory allocation 1. We've been talking about virtual memory up to this point. One of the things we looked at it early on in the class is how do you allocate data objects from your program? What we haven't looked at yet is how is the allocator itself implemented. So when your program calls a malloc or a free call, the standard memory allocation library does something underneath. What we're going to talk about this week is essentially how does that allocator work and what are the different things you want to optimize and what are the systems engineering issues you have to deal with when you build this allocator. The following set of videos are quite important for the memory allocator assignment. So first, let's start off by just refreshing our memory on all the different ways you can store program data. So you could have static global data. So like in this case, array, which is we declared right at the top. All of the size is known at compile time. The duration of the allocated region is the entire lifetime of the program. That is, it's going to exist as long as the program is running. And some of the portion could be read-only. You then have stack allocated data. So these would be temporary variables that are declared inside a function. Again, the size of all of these variables is known ahead of time, so the compiler kind of manages them. And managing it means issuing instructions when a function starts up first to create space on the stack. The piece that we haven't looked at yet is how is dynamic heap data managed. We kind of looked at the interface early on in week 2. So if you're not familiar with the interface, do not worry. I'm going to refresh it in the next few minutes. In this case, the key challenge is that the size is only known at runtime. It's based on the user input, so it could be dramatically different between two different programs. So imagine a web server versus something just manipulating strings. Web server allocations are going to be much larger. And the other problem is that the lifetime of the data is actually quite unknown. So the program is going to insert malloc and free calls, and you don't know where they're going to insert these calls. And so again, it makes it really challenging to manage. C++, new, and delete have the similar issues as well. In fact, underneath they are implemented using a combination of memory allocators. So first, we're going to introduce dynamic memory allocation, the goals, and then start talking about the general strategies behind allocation and deallocation and the challenges you kind of have to deal with. First, so dynamic memory allocators are essentially a library that kind of manages the virtual memory at runtime. So they are there for helping allocate and deallocate data structures or data objects whose size is only known at runtime. And effectively, they manage the heap of a process's virtual memory. So a large fraction of your memory space is given to the heap. It's just a giant chunk of bytes. And your allocators is simply in response to malloc calls, simply vend out chunks from this heap space and return the pointer. So the general idea is that it just has to manage the space in a way that's efficient. We'll look at some of the goals of any typical allocator in a few slides. There are two types of allocators. There are explicit allocators. That is, they allocate or deallocate space for data objects in the program based on explicit malloc and free calls. These are effectively calls you're making in your program based on the data that you think you need. And so in this case, you're explicitly managing the space. So the allocator is not going to free anything unless you tell it to free it. It's not going to allocate anything in this or vend out any chunks unless you explicitly tell it using a malloc call. Implicit allocators, on the other hand, do not have any such library calls. Essentially, as your program uses different data objects through the lifetime of the program, the allocator is going to always be on. It's going to simply kick in and figure out what is the data's lifetime and when it should be allocated, when it should be deallocated. The allocator is implicitly figuring out all of this on the fly. This is also in most popular languages known as garbage collection. Some examples of these would be Java, OCaml, and Lisp. Python's also one of the key overheads in the Python language is garbage collection or implicit allocation. So the dynamic memory allocator, simply the allocator organizes a heap as a collection of variable sized blocks. So essentially what it's going to do is you have your heap, and at some point in your virtual memory system, so right, and it grows upward. What it's simply going to do is, in response to memory allocation calls, for example, a program could allocate 40 bytes, and then later on it could allocate 50 bytes. What it's simply going to do is vend out chunks from the heap in response to these malloc calls. And since the amount of data that's required will vary from malloc call to call, because different data objects require different sizes, the whole heap itself is organized as a collection of variable size blocks. So for example, the 40 byte chunk could be this red chunk, and then you could have another chunk that's 50 bytes, right? And this is a completely different size than the red chunk. So the starting and ending address of each of these chunks will vary from chunk to chunk. And so this is one of the first challenges that you kind of have to manage. And as you free these blocks, there's also going to be free space in between these blocks. And again, these also are of different sizes. So it's almost like packing the bag problem, where you've got all of these chunks and you kind of have to pack them all into a continuous byte array, which is the heap. And so this is one of the major challenges with just writing a memory allocator. The other challenges, so inherently remember that the operating system is the one vending out actual space. So you need to create virtual to physical mappings. So the allocator also has to deal with the operating system and make the appropriate library calls. Finally, application objects are typically smaller than pages. So remember that virtual memory system can also be thought of as a memory management system, right? Because you're essentially allocating physical space in blocks of pages, right? Which are 4 kilobytes. But in that case, all the space that's allocated is in the 4 kilobyte chunk. Whereas in this case, the program objects are all varying in size, and they're also much smaller than pages. So you're allocating a lot of small objects in a contiguous space. And in this case, the space is also big, because while physical memory is of the order of 2 to the, so maybe you have 16 gigabytes or, up to 1 terabyte these days in some of the biggest server machines. Your virtual memory space potentially is 2 to the 32 or 2 to the 64, right? So this is a huge space. And so mapping or your heap space is huge, and you're trying to allocate chunks within this space, right? And so there are certain techniques that just are not feasible. For example, you couldn't use a bit for every page to indicate if it's free or not, because in a virtual memory space, even 1 bit per page, that data structure is going to be pretty big. So now let's look at the actual C interface for these calls. We looked at these in more detail in week 2. So if you are not really comfortable with this, then pause the video, go back and take a look at the week 2 videos. But this is a quick refresher of the interface itself. So the first one is the malloc. So malloc just takes a single parameter, so just size t. Size t is just unsigned in. So just it is a how many bytes do you want to allocate. So the return type from a malloc is just a void start pointer. So the pointer doesn't have any type. So typically the way you would do this is if you cast it in the following fashion. So you call your malloc and then cast it to the type that you want. And subsequent to this, now pointer is a object or in a stack or in a global, which is pointing to this allocated space. Okay, so you have a entry which is pointing to this actual allocated space. This is pointer, and anytime you want to access this piece of data, you have to go through pointer. So size of makes the code more portable by actually deriving the size of the primitive types. We can kind of keep the program running on different, we don't have to rewrite the program if we move from 32-bit to 64-bit or across different machines where ink could have different sizes. Void star is implicitly can be cast into any pointer type, which is why it's returning a void star, right? So it allows malloc to be compatible with any object that you want to create, right? So you don't have to need a separate malloc for any object type. So you can kind of create it for, you can invoke malloc for any object type as long as you know how many bytes that object's going to require. Yeah. Sometimes the cast could be implicit, but explicitly type casting will also help you catch errors. Finally, if malloc is not able to allocate the space, it's going to return a null saying that it's a failed request. And also the amount of space that's allocated is going to be contiguous. So any size that you require is going to be continuous in memory or in your virtual memory. And this is kind of where the challenges start to appear, right? Because if you had free space of 20 bytes and another free space of 20 bytes and the rest of it has been taken away, yeah, malloc's going to fail because both of these regions are non-contiguous. So one of the first rules of the malloc is it can only return a pointer to the beginning of a block which is continuous. Okay. And finally, it also needs to figure out where to exactly place this block or the start address to place this block in. So it's typically aligned to 8-byte or 16-byte boundaries on an x86 processor, and irrespective of the type that it's returning for. So it doesn't matter what the type is, it's either going to align it to 8-byte or 16-byte, since those end up being the largest primitive types in your C program. Calloc is a simple addition to malloc. Basically, it zeroes out the chunk along with just allocating the region. There's a subtle difference in that essentially by zeroing it out, you kind of make it easy for the programmer in terms of what values they can assume in it. But generally speaking, it's kind of the same thing. Realloc is slightly different. So in this case, you've already allocated some region and you want to either grow the size or shrink it, and so realloc is used for that. SBRK, which is pronounced as sbreak, is an internal call. So in this case, sbreak is made between the malloc library or the allocator library and your operating system. So essentially, it's used by an allocator to get more space from the heap. So the general idea is that your allocator is called into your operating system and it's going to grab a bunch of pages from your heap, and then what it's going to do is it's going to allocate space from this region that was given to it by the operating system. So this is the space the operating system is still managing. This is the space that's been, the operating system is allocated and the malloc is kind of managing. And any region that the program wants to allocate, malloc is going to reserve those chunks in this malloc managed region and then return the pointer, the start address of the chunk. The final interface is freeze. So free basically releases a chunk back into the free pool of available memory. So one of the things to note is that the address taken by P must be the original address returned by a malloc, calloc, or realloc. So malloc, once it allocates a chunk, is going to return the start address. You can think of the start address as kind of being a tag. So you have every chunk is tagged with this start address. Right? How exactly we're going to store these fields in data structures, we'll look at in a second. But effectively, every chunk is tagged by the start address, and the pointer that you pass in is this start address, right? The start address of a chunk that was previously allocated by malloc, calloc, or realloc. You cannot pass some intermediate pointer, otherwise it's going to cause a seg fault or it's going to crap on you, saying it can't find what to free. If you call free on a block that's already been freed, that's an error. So double frees are bugs. Make sure that you malloc, calloc, or realloc before you try to free. So if you haven't allocated a block and you just try passing arbitrary pointers to free, again, it's going to complain. So this is what your memory allocation in C kind of looks like. So this is a pretty simple example. So you've got I, and then you've got a pointer P, and you allocate n elements on the heap. You check if the pointer is null. If it's not, that means the allocation succeeded. In this case, you've got n multiplied by size of int bytes, and it means you've allocated an array of n elements where each element is an int. We cast it to P, and now remember that array names can be used as pointer for pointer arithmetic. So in this case, P can be used just like for array indexing. And so you're setting P of I equals I. So this basically sets the value 0 to n minus 1 for each of the elements of the array. Once you've done that, you reallocate the array. So in this case, you're growing the size of the array from n to m. We assume that m is a positive value, so it's actually growing the size of the array. Once we do that, we iterate from n. So the array is already been initialized with value 0 to n minus 1. We've added a further m elements to this, so we now have to go in and fill those elements. So n to n plus m minus 1, which is what we're doing up here. And then finally we print out the reallocated array, so the entire array, and then we free it. So notice the pointer that we're passing to free, which is P, and P has been updated by the realloc call. So once you have an intermediate realloc call, now in order to free the whole array, you have to pass the updated pointer. So because a realloc call could potentially even move the array or do something internally. And so the only parameter that you can pass is the value that's returned by the realloc. That is, the malloc's return value for the pointer, or where the chunk is, has been kind of superseded by the realloc's call. So before we start off, we're now ready to start taking a look at the actual memory allocator, and then start seeing what are the different goals of the implementation, what are the challenges, and the different systems engineering issues. So before we do that, let's have a visual representation of how we look at memory. So in this case, this horizontal array is representative of memory. Each square, you can think of it as a box of 8 bytes. So in this case, we are allocating data in multiples of 8 bytes. Okay. Some of the references in the textbook could potentially be 4 bytes. Just watch out for that. This is a result of the textbook being written a while back. So an allocated box is going to be indicated by a shade. So in this case, we've allocated 4 bytes. A free block is indicated by white space. Okay, so you've got, if it's a white space, that means it's a free word. So here's an example. So if I here the first call to malloc is allocating 32 bytes, or 4 words, each word being 8 bytes. The next one allocates 5. The next one allocates 6. Note that in these cases, the mallocs, we're just allocating them one after the other in a contiguous fashion. This is not necessarily guaranteed. For example, these 40 bytes could have come potentially from a later portion of the array itself, or the overall heap. There's nothing that says that subsequent mallocs in sequence have to go to continuous regions in memory. In fact, you should make no assumption about the relationship between P1, P2, and P3. We then free P2, so which means the blue region is going to go. Okay, so now your array looks something like this, and the total amount of free space in this array is 1, 2, 3, 4, 5, 6, 7. So we've got 56 bytes free in this array. Now let's look at the implementation interface. So your applications can issue arbitrary sequence of malloc and free requests. One rule is that the application must never access memory that's not being currently allocated. And the other rule is that must never free memory that's not currently allocated. So malloc and free go in pairs. So you should never issue a free that you've not mallocked yet. There are a few rules for the allocator. Allocators can't control the number or size of the allocated blocks. Okay, so those are issued by the programmer. Allocators must respond to immediately to malloc. It cannot buffer it. The malloc calls have to be responded in the order in which it comes from the program. So if you have a malloc followed by another malloc in your program, the pointer responses to that will be in the order in which the mallocs are in the original program. Allocators must only ever allocate blocks from free memory. So there's a notion of memory that's allocated and then ones that are free. Blocks cannot overlap, or the allocator can't choose to simply overlap blocks if their contents kind of are similar or are the same. You always have to give each memory malloc call a separate block that's isolated from other malloc calls. You must align the blocks so that they satisfy all alignment requirements. So we looked at alignment again in week 2. So you've got to look at what are the specific alignment requirements for the particular machine for the program, and make sure that any allocation you make satisfies those. Typically by ensuring or by using the worst case alignment constraints. So for instance, on a 64-bit machine, you would do 8-byte alignment or 16-byte alignment. You can kind of ensure that you kind of meet all alignment requirements. And finally, you must not be able to move the allocated blocks. So if blocks are allocated and you think that there's a better way to manage them, you can't move them around. This is because, let's say you have your program. So the final one is kind of a really important constraint. So here's a way to understand it. So let's say you have your program and you say p equals malloc, and then you're going to continue to use p. So now this is your library and this is your actual memory. So this is your malloc library. So initially it allocated this chunk and then returned this pointer. Now p is storing this value. So let's say it allocated address 0x10 and it returned 10 to this. Now subsequently you are using p assuming that this address 10 has been allocated for this particular data object. So if the allocator, without informing the program, suddenly moves this here, then this address within the program is no longer valid. Remember that the program has taken the pointer that was returned by malloc, copied it into a local stack or global variable, and is using that pointer to kind of access this data element. Okay, so it's created a local copy of the value that was returned by malloc and is remembering that value. Now, if your malloc moves it, it has no way of going back to the program and then telling it, oh, the pointer p that you previously used to think is 0x10 or the data object is now being moved to 0x100. It can't do such things because there's no callback from your library into your program. Because every function call in your malloc, your program can call into it, but your allocator can't call back into your program. It doesn't understand what the program is even, right? And so in such cases, it's going to break the pointers if it decides to move the allocated regions around. And so essentially an allocated region, once it's been given back to the program, is going to persist and is going to remain in the same place until the program decides to free it and return it to the unallocated or free region. Though you cannot move allocated blocks during the duration of the entire program. What you can do is, once the block has been freed, then reallocate it in response to a different malloc call. What are the performance goals of an allocator? So let's look at that. So a lot of the systems engineering and the cleverness or the smartness of when creating allocators is in response to specific performance requirements. So what are our performance goals? Broadly speaking, there are two. The first one, throughput and utilization. And these goals are often conflicting. So let's look at throughput first. Throughput is simply how many memory allocator requests are you going to complete per second or unit time. So if you have 5,000 malloc calls and 5,000 free calls, and they complete in 10 seconds, then the overall throughput is 5,000 plus 5,000 divided by 10 seconds. So 1,000 operations per second. So how many memory allocator memory interface calls are you going to complete in a fixed amount of time? The note that we consider both malloc and free calls. So you cannot build allocators where one is arbitrarily faster than the other and then claim good performance. You need both to be equally performant. Another goal is space usage is more related to how you effectively manage space. And in order to manage space, let's introduce this term called a payload. So a payload indicates the amount of space that's actually really used or required by the program. So when you call malloc, so let's say you call malloc 40 bytes. In your heap itself, the malloc's going to allocate 40 bytes plus a delta. Okay, the 40 bytes effectively is the payload. So this is the space that was requested by the program itself. The delta, the allocator requires kind of to manage the space of within the allocator. It's also required to satisfy alignment issues and a whole host of reasons why it might add this delta. That is, it uses more space than what the program required. And so in such cases, the delta is technically waste. So one of the things allocators worry about or are concerned with and hope to optimize is this wasted space. So they hope to have as little wasted space as possible, right? This is particularly important when your payloads end up being really small, like in many programs, right? So most often, you're not necessarily just trying to allocate arrays or large data structures. You might allocate just small ints. And so as your payload starts to get smaller, this overhead starts to grow. So in order to look at aggregate payload, the aggregate payload is given a set of requests, RK, R suffix K. The aggregate payload is the sum of all currently allocated payloads. So simply, you'll take all the malloc calls you make in your program. For example, let's say there's another malloc call and this made 20 bytes. The aggregate after these two calls is 60 bytes. You simply add up all the allocated requirements of the program. So HK is the actual size of the heap, and the size of the heap can be increased using sbreak. So the utilization UK is essentially the aggregate. So in your program, you have malloc calls that are being made. So in this case, it's 2, there's 3. So as you go through these, you figure out the max PI or the max aggregated payload, as I varies from for all I less than or equal to K. And so after K plus 1 request. So you find out, okay, after 1 request, what was my aggregate payload? What was the aggregate payload after 2 requests? What was the aggregate payload after 3 requests? Right? And you find the max of that value. Okay? And so at any given time, how much space did the program really require? So max PI, I less than or equal to K, effectively the intuition behind it is you're trying to kind of figure out how much space did my program require at its most extreme point, right? What is the maximum space did my program ever require? Because remember, the amount of memory required by a program varies over time. So let's say that your y-axis is memory required, x-axis is time, right, as the program's running. And so memory required is typically going to start at 0. Initially, the program requires nothing. Then as it allocates, it goes up, and then it comes down. Right? But there are many different curves. For example, it go up, it could come down. Right? So as it allocates and frees. So this would be cyclical. Would be an example of case where the program's allocating and freeing repeatedly. And the mountain example would be a case of where the program keeps using more and more space until it reaches a peak point. Then it starts freeing all the space. Right? And so the Utilization factor is basically trying to figure out the peak point of the program. That is, in the worst case, how much space did the program actually require? And that is on the numerator divided by the actual heap space. How much space did the allocator get from the operating system? So remember that the allocator library is sitting between the operating system and the program, right? So the program requests some amount of space to the allocator. The allocator invokes sbreak and requests some amount of space from the virtual memory space, so some amount of pages from the operating system, right? So what we're really trying to measure is how much space did the program really require and how much space did the allocator ask the operating system for, right? And we want to maximize this, right? So we want to ensure that the space requested from the operating system is effectively the same amount as the space on the heap, or that the program manages to use everything that it was given, and that the allocator does not ask the operating system for any more than what the program required. Right? Why is this hard, and what happens to the throughput if you're trying to do this is one of the issues we're going to be dealing with. So the main reason this is hard and it affects throughput is that there is fragmentation. Right? So poor memory utilization is caused by fragmentation predominantly. So fragmentation basically refers to sections of the memory that are not storing anything useful, that is, they are free space, but cannot satisfy any allocation requests. Right? So for example, we will look at a particular example in a second, but essentially there's free space in the heap, but the program is not able to use it. There are two types why this kind of fragmentation occurs. So one is internal fragmentation. So internal fragmentation is wasted space inside a struct, right, between fields due to alignment. Again, this is something we dealt with in week 2 as part of the class when we spoke about structures and multi-dimensional arrays. So I would cross-refer you to go back and take a look at this video as to why we do this. But effectively, there's cases where the program requests a certain amount of memory from your allocator, but then it doesn't really use all of that space for storing meaningful data. Some of that space is just padding that has been added to kind of make sure that the program data kind of aligns up on certain address boundaries. And so this space is technically wasted because internal to the allocated region itself. So the allocator gave back 40 bytes, but the program really used only like 20, and the rest of the 20 was just padding, right? So this is wastage within the allocated space, and this is known as internal fragmentation. External fragmentation is caused by wastage between allocated regions, right? And this is potentially due to the combination of allocation and freeze, and we'll look at a particular example in a couple of slides. So here's an example of an internal fragmentation. So your payload, which is the actual usage by the program, is smaller than the gray region, which is the extra stuff that's been added around the block. A few different reasons. So one is padding for alignment. So alignment is the most common reason why you have this. Also, your heap could only allocate certain sizes. Maybe it doesn't allocate all possible allocation sizes. And so in these cases also you may add padding. So the program heap allocator may only allocate 16 bytes, right? And if your program requires anything smaller than that, it's still going to give you 16 bytes. Right? And then this would be an example of returning a big block to satisfy a smaller request, right? Just because the overheads of the heap data structure might be high enough that it might not be worthwhile satisfying a smaller request. They kind of cost the same. Then there's the overhead of maintaining the data structures themselves, right? Remember, the allocator needs to maintain data structures for just figuring out where things are allocated. So for example, remember when you malloc, a size, you specify how many bytes you want. There's a pointer that's returned, and then you just call free p. You don't actually say how many bytes you want to free at this pointer. So at the bare minimum, you kind of have to remember the association between how many bytes was requested and the pointer P. So you kind of need a pair, right? The pointer and the size, and store it internal to the allocator. This is not going to be stored as part of the program, right? So that's going to require some space. And so this is all examples of fragmentation caused due to these issues. And this is kind of easy to measure and quantify, because in this case what happens is that it depends only on past requests. So you basically look at the request, and you can kind of say what the overhead is going to be. External fragmentation occurs when holes happen due to the interaction between mallocs and frees. And so in this case, these combination of mallocs and frees leaves holes between the blocks, and the aggregate payload is non-contiguous, and hence the allocator cannot basically allocate the space, right? And this can cause a situation where the aggregate, there is enough free space in the heap to satisfy a request, but there is no single block. There's no one contiguous block that's big enough to satisfy the request. So going back to the same example that we had previously, we allocated 4 8-byte segments, we allocated 5 8-byte segments, and then 6 8-byte segments. And then let's say we invoke free P2. So now we have 5 8-byte regions that are free, and then another 2. So totally we have 7, and we totally have 56 bytes that are free in this heap right now. And now you have a new allocation call from the program that only wants to allocate 48 bytes, right? So you do have this free space in your heap. However, the malloc is going to fail. This is because it wants 48 bytes. Not only does it want 48 bytes, it wants 6 contiguous squares, each of 8 bytes. But we don't have 6 contiguous squares. We have 5 contiguous squares and 2 contiguous squares. So we cannot actually make this allocation, and we're going to fail. And this is because we don't know, and estimating this kind of external fragmentation is really hard, because we don't know what future requests will be. It's difficult or impossible to know if past placements will be problematic. So the entire history of these allocations and frees and the particular program characteristics can exacerbate the situation. Okay? One potential solution is to try to create contiguous space even before this malloc call comes. That is, figure out a way to concatenate these two and move them somewhere else, right? And if you could do that, then maybe the problem could be solved, right? Sometimes you could have free space that are right next to each other, right? You could potentially concatenate those together to create the space. In this particular case, these two you can't do anything about, because if you try to make them contiguous, you'll have to move one of these other allocated regions. And one of Malloc's rules is you can't do that. You can't move any allocated region. And so in this particular example, there's not much you can do.